Okay, so the question reads, evaluate the surface integral over the parallelogram with those parametric equations. X is u plus v, y is u minus v, and z is 1 plus 2u plus v. So in other words, we do have our parametric equation for the surface as being u plus v. So let's write this as a function of u comma v being u plus v in the I, u minus v in the j, and 1 plus 2u plus v in the k. So instead of writing ijk, I'll just write it in a vector notation. And we are given the bounds on u and v. So the way we do this is we know that our double integral on surface S of x plus y plus z ds is the same exact thing as f of r of uv dotted with the ds. It can be shown through some geometry derivations. It's equivalent to saying ru, which is the partial of r with respect to u, crossed with rv, partial of r with respect to v. Take the magnitude of that cross product and multiply it by dA, where A is the region of the area of region D that we will be integrating. Okay, so RU is partial of R with respect to U, so that will be 1, 1, 2. You hold V constant, and you differentiate with respect to U. And likewise, for RV, you hold V constant, so now you hold U constant, you differentiate with respect to V, the vector R. So this is 1 minus 1, 1. And then if we do take the cross product of these two vectors, I'll just do the cross product here once just to show you. And then on the if I post more problems on this, I will skip it since I've already mentioned it once. So I, j, k, 1, 1, 2, 1 minus 1, 1. So you hide the first and row and first column. You take the determinant of that matrix. So that's 1 plus 2. That would be 1 plus 2. So that in the I minus. You hide the second column first row and you take the determinant of the remaining matrix. So that matrix is 1, 2, 1, 1. So you get 1 minus 2j. And hide the first column, third column, first row. Take the determinant of the matrix 1, 1, 1 minus 1. So we get plus minus 1 minus 1. So okay. So the cross product will be 3, comma 1, comma this is a 1 here, negative 2. And then if we take the magnitude of that cross product, that's just the sum of the squares of the components. So 9 plus 1 plus 4. So that would be root 14. And then we can plug this in with f being, this is our FRV, so now we get the integral to become x is u plus v. So we replace x, y, and z with their components in terms of u and v. So u plus v, y is u minus v, so plus u minus v, and I'm substituting in the integral star there. And z is 1 plus 2u plus v. And then this is multiplied by the magnitude of the cross product, which is root 14. And then dA is just du dv. It's the area of the subrectangle that we take for the Riemann sum from which this formula was derived. And we are told that u goes from 0 to 7. So this will be our bounds, 0 to 7. And v goes from 0 to 6. And this is, of course, a straightforward integral in u and v. You integrate first with respect to u from 0 to 7, then you take that answer and you evaluate it. You integrate it again with respect to v from 0 to 6. I won't worry about the details of the integration. If you need help on that, you can check my videos on basic calculus 1. For this class, I'll assume someone who is watching this is familiar with the details of an elementary integral. I will just give you the answer, which turns out to be 756 root 14 after I did it on Maple. And I worked it out by hand just initially, but then confirmed it on Maple. I always work out my integrals by hand, and then to make sure I use some kind of digital software to confirm the correctness of the answer. This concludes this question on how to evaluate the surface integral on a parallelogram with a given parametric equations. Thanks for watching. Please don't forget to comment and subscribe if you want, and like.